of gives a feeling that, you know, you need to compromise on merit or on quality if you're talking about women. And therefore, I think it's very important for women to understand that um, they have to face competition without any reservation, and they can actually make their way through. You know, they do not need some kind of reservation of that kind to win awards. You can actually get positions and win awards without any such reservation. So Margaret Burbridge continued her work, and she also played very important contributions to the Hubble Space Telescope, where she helped develop the faint object spectrograph. That's a very important instrument that is there on the Hubble telescope. And as well as she also discovered the supermassive black hole at the center of Messier 82. So Margaret Burbidge, like I explained, does have some very important aspects of her life which are really worth appreciating. If we move ahead, we come to another very well known woman who also played a very important role, and that's Vera Rubin. Now, what makes Vera Rubin's life very, very important and very good as a role model, not only to women, but to all astronomers, is the important discovery that Vera Rubin made. Now, Vera Rubin, she actually was observing what are called the galaxy rotation curves. So, this is a rotation curve in the sense in which you plot the velocity of stars versus their distance from the center. Now, if stars were to follow normal Keplerian rotation around the center, then rotation would fall with the gravitational law as a 1 by r squared, right? So, as you go to stars away from the center, their velocity should fall as a 1 by r squared, right? But what actually Vera Rubin observed when she observed galaxies is that she found that instead of the drop in velocities, there seemed to be a mild increase in velocities, right? There was no drop, it was either consistent or it was mildly increasing, which was something very, very strange, right? And this was very strange because, like I said, as per Keplerian, rotation, you should have a 1 by r squared law, while you were having this very strange kind of a flattening of the rotation curve, which basically implied that there was some kind of matter in the outer regions of galaxies. And that's when Vera Rubin came up with a very revolutionary idea, and that was the idea of the existence of dark matter, right? Now, dark matter is very, very strange. It's called dark because there's no emission from this matter, right? You do not see any emission, but in terms of gravitational force, you see the stars in the outer regions moving with large velocities. So, dark matter is matter for sure, but it is dark. It does not give any emission. And I think we have to give Vera Rubin credit for actually openly declaring the result that she got while when she checked and counter checked her results of her observations. She was confident that her galactic rotation curves were correct, and that's when she proposed the existence of dark matter. Now, in today's times, we do know that dark matter does definitely exist, but for Vera Rubin's times, when it was a totally revolutionary idea, this was something totally which was counterintuitive. It was totally against the science of those times. Vera Rubin stood up to her observations and her theory of dark matter, which is also something very important, like I said, not just for women astronomers, but for all astronomers. That the biggest thing in science is observations. And from your observations, you develop a theory. And you always have to, if your observations do not satisfy your theory, then your theory definitely needs to be changed, right? And that's what Vera Rubin did when she proposed the existence of dark matter, right? You had to have this kind of a case to, do this thing. Now, there are also a whole set of women who played very important contribution, and these were called the Harvard computers. Now, in Harvard Observatory, the Smithsonian Astrophysical Observatory, what happened is this was 100 years ago. So observations were taken on large photographic plates. Now, at that time, the director was Edward Pickering. Now, the job that had to be done was one had to use these photographic plates to very carefully catalog the data obtained on these photographic plates, right? To very carefully measure the positions, the brightness of these objects, tabulate them, and put them in a systematic manner. Now, at those times, this was something which was considered, very monotonous and not very interesting for the men of those times. And at that time, Pickering came up with an idea of hiring women as skilled workers to actually do this kind of work. Now, this was very meticulous, monotonous, tiring kind of work, which included hours and hours of analysis of data. But the women who actually did this work were people like Annie Jump Cannon, Henrietta Leavitt, Cecilia Payne, Antonia Maury, and all these people. They actually, when they meticulously handled this data, they discovered something which was very, very important. Now, in those times, Pickering was kind of mocked by the community for doing it in this way. And all these women were actually called Pickering's harem, right? Because he had only women over here who actually did this work. But these women, like I said, came out with very important results. So, for example, let's come to the first case of Henrietta Leavitt. Henrietta Leavitt was actually seeing the observations of variable stars, which are called Cepheid variables. Now, Cepheid variables are pulsating stars. So, what happens is that these stars increase in brightness and fall in brightness. There's a period with which their luminosity grows and falls. And what's interesting is that there is a period luminosity law. Okay, that means if you can actually measure the period of variation or pulsation of a Cepheid variable, you can actually obtain its absolute luminosity. Okay, so that's what Henrietta Leavitt did. That she observed Cepheid variables, used the photographic plates to tabulate their variation in brightness, measure their periods, with which she could measure their absolute luminosity. Now, when you observe the variable, you observe what is called the apparent luminosity. And the difference between the apparent and the absolute luminosity is what will give you the distance to those stars. So, Henrietta Leavitt, she actually managed to measure the distances to these Cepheids. Now, Cepheids are very, very bright stars because they are giants. They are very, very bright. And therefore, we can actually observe Cepheids in other galaxies, not our own, but even the outside galaxies. And this is something very important, which was actually used by Hubble. So, galaxies we know are a large collection of stars, gas, and dust, right? What Hubble actually did is Hubble looked at the spectra of various galaxies using the Mount Wilson telescope. And using that, when he measured the spectra, he used the Doppler effect. What is the Doppler effect? That if you have a moving source of light, which is emitting radiation in a certain wavelength, depending on the velocity of this source, you will have a shift in wavelength. Okay. If the source is moving away from you, the shift will move toward the redder side, that means to longer wavelengths, while if the source is moving towards you, it will move towards shorter wavelengths. So what happens is if you can measure the shift, right, you can actually measure the velocity of the source. So that is exactly what Hubble did. Is he observed the spectra of these galaxies and measured the velocity of these galaxies. And using this, as well as the data of Henrietta Leavitt for the galaxies where he observed, he looked for Cepheids, and using the Cepheids, he had the distance to those galaxies. Using that, he obtained this law, which is called Hubble's law, which is V is equal to h naught into d. V is the velocity of the galaxy, d is the distance of the galaxy. So the V value was found by Hubble using the spectra, and the d value was found by Hubble using the Cepheid variables, which Henrietta Leavitt had discovered and found the distances to. So based on this, Hubble actually wrote this thing, which is V is equal to h naught into d, where h naught is called Hubble's constant. And therefore, this means this. Look at this figure over here. This is the Milky Way. You can see as the distance of the galaxy increases from the Milky Way, its velocity increases, right? And therefore, more distant galaxies have larger velocities and closer galaxies have smaller velocities. Now, if you play this whole movie in the reverse, this basically tells you that the universe was all sitting at this point, after which you had what we call the Big Bang, and the expansion of the universe started, right? So this is the very basis for a very important cosmological theory which we have of the universe, which is the theory of the expansion of the universe. That means we say that the universe started off with the Big Bang, after which the universe started expanding, and you had these velocities based on the observations of these galaxies. You could actually measure Hubble's constant with which the expansion took place. But obviously, you can see that at the basis of this discovery is Henrietta Leavitt's values of D, because the D was found in an independent fashion and the spectra was found in an independent way, right? Um, so this is the very basis of Hubble's law, which, like I mentioned, is the basis for the expansion of the universe using the spectra of galaxies, right? Another very important Harvard computer was Annie Jump Cannon. Now, Annie Jump Cannon, what she did is she observed the spectra of stars, okay, not galaxies, but stars. And let me just show you. This is what the spectra of stars look like, okay? So when you actually observe it in a photographic plate, you will see something like this. This colored part is the continuum, which is the spectra which ranges all wavelengths. And on the continuum, you can have what are called either emission lines or absorption lines. If you have emission lines, you'll have bright lines. Or if you have these dark lines, these are called absorption lines. So using this, you can actually make a plot like this, which is a plot of intensity versus wavelength. So what Annie Jump Cannon did is that using the photographic plates of the spectra of stars, she actually plotted the spectra like this. So like I told you, intensity versus wavelength, you have these dips, which are these absorption lines, right? And what she did is looked at the spectra of thousands of stars. Okay, you can see over here, this is the instrument through which she's actually looking at the photographic plates. You use magnifying glass, you magnify it, and actually look at the photographic plates. And using that, she actually managed to categorize the stars based on their spectra. Now, look at these spectra. These spectra they are very, very rich. You have so many spectral lines. You see, as the star becomes colder, you have more and more spectral lines. Hotter stars have lesser spectral lines, basically only hydrogen and helium. But as you go to colder lines, you'll have magnesium oxide, titanium oxide. You have various other elements also showing up over here. And what Annie Jump Cannon did is she categorized these stars based upon their spectra. Later on, it was realized that this spectral classification could be also related to the temperature of stars, based on the same thing which I told you, that hotter stars do not have too many elements in their spectra because they are so hot. So the stars only have hydrogen or helium. But colder stars then have even more elements like titanium, magnesium, calcium, various other elements which could be there, potassium, etc. So what Annie Jump Cannon did is she actually categorized the spectrum, which is really a very difficult job to actually do. Another very important person amongst the Harvard computers was Cecilia Payne. Again, Cecilia Payne came up with a revolutionary theory. What was considered at those times is that the universe was made up of a composition like the sun, right? Like the sun or like the earth. Now, what Cecilia Payne is did when she looked at the spectra of stars and she saw so many lines of hydrogen and helium, the results of her doctoral thesis was that basically stars are more made up of hydrogen and helium, and that the bulk of the universe is just hydrogen and helium. Now, in those times, this was obviously considered to be a very revolutionary idea because it was considered to be against the norma, right? This is not what people thought was true. But Cecilia Payne made she made these results, inferences, basically based on the observations which she had, right? And again, like the case of Vera Rubin, where Vera Rubin, double checked her observations. She was confident about her observations. Based on her observations, she concluded that there is dark matter. Similarly, Cecilia Payne also concluded that the universe is made up of hydrogen and helium. And finally, it was realized that she was actually very, very right, though this was against the science of her times, right? Now, let's move a little further on. Let's come out to Joycelyn Bell. Now, Joycelyn Bell, she was actually a PhD student at the University of Cambridge. And she worked with Anthony Hewish. She was actually she constructed a radio telescope. The radio telescope was made basically to study interplanetary scintillations, to study quasars. Now, while she was doing her observations, she actually got some kind of pulsating signals from some sources. Okay, there was a periodic pulse, a periodic signal. Now, at that time, it was wondered how did she get a periodic signal at that time, and therefore it was also called the signal from the little green men. Okay, because it appeared that something of that kind, that you have these little green men who are giving these pulsating signals. Now, later on, it was realized that these were not artificial signals; these were natural signals from a certain class of stars, which are called pulsars. Now, pulsars are stars which are stars in a very later stage of evolution. So, what happens in those stars is that they kind of collapse with their own weight, okay, and therefore they rotate at a very large velocities. And these stars have a very strong magnetic field, and because of the magnetic field, radiation from that star cannot come to you from all through the surface. It only comes from the poles. Okay. So as the star rotates, you only receive the star is of a very small size, barely 10 kilometers. So as the star rotates, you get the pulsating signal coming at a very short frequency. There are even millisecond pulsars, very small, short frequencies. And this was obviously a very it was a breakthrough discovery of pulsars. And but again, the Nobel it was Nobel worthy, so the Nobel Prize was given in 1974 for this discovery. But unfortunately, the Nobel Committee decided that they will only give the award to her supervisor, Anthony Hewish, and they did not give Joycelyn Bell any credit for her discovery, because they basically stated that this was done under the PhD supervision of Anthony Hewish. However, we should remember that when Joycelyn Bell did her work, it was not that Anthony Hewish had expected the detection of such a signal. The signal that was detected in a purely accidental, as a pure accident. What they were supposed to be detecting was the interplanetary scintillations, right? So what they actually discovered was an accidental discovery, which Joycelyn Bell verified and re-verified to confirm her observations. But the Nobel Committee refused to acknowledge her contribution, and hence they gave the Nobel Prize only to Anthony Hewish. 50 years after this happened, okay, it was 50 years after that she finally, the breakthrough prize was actually given to her, which is worth $3 million, and which finally went to Joycelyn Bell. And Joycelyn Bell, all through her life, has been working very hard about this problem about discrimination towards women, and therefore she contributed her complete prize money to basically fund PhD scholarships to underrepresented physics students in her country, as well as to basically handle diversity issues where not everybody gets a chance to study astronomy, and was basically supposed to fund women in astronomy using her breakthrough prize. So she contributed it all to that. In more recent times, we now come to Andrea Ghez. Andrea Ghez actually got the Nobel Prize in 2020 for a very important discovery. She actually made very meticulous observations of the center of our galaxy in the near infrared using the VLT. And we know that our center of our galaxy actually has a supermassive black hole. Now, a supermassive black hole has a very strong gravitational force, and therefore stars near the center of the galaxy, they move with a very large velocity. Now, what happened is, one of the closest stars to the center is a star called S2, and it has a period of about 20 years. So what Andrea Ghez did is that she observed this star and observed it for a period of more than 20 years to actually map out its orbit. And by mapping out its orbit, she could calculate its velocity and calculate the mass of the supermassive black hole at the center of our galaxy, which she found to be about 4 million suns. And this very discovery is for what Andrea Ghez got the Nobel Prize in 2020. And she's the fourth woman to have got a Nobel Prize in physics. And that's a very important discovery. And so amongst the four female Nobel laureates in physics, Andrea Ghez is the only astronomer who's actually got the award. Right? So So this was all about women all over the world. We did not talk about India, but obviously there are women in India also who are playing a very important role. So let's look at back home in India. Most of you all have seen these pictures of women in ISRO, cheering after the Chandrayaan, the Mangalyaan mission, and people are aware of the large contribution made by women in the Indian space program. So the Indian space program has a lot of women who are actually working as engineers, as project scientists, as project leads. They're actually handling a lot of the projects and playing a very important role in the space program, right? So there are various women over there. If you were to mention a few, for example, there's Veera Lata Ambika, who's actually leading the Gaganyaan mission. If you remember, there's a mission which is called Gaganyaan, which is about sending out man and hopefully a woman in space by India. And this mission is actually being led by Lata Ambika. And this is being done in collaboration with Russia. And hopefully, in a few years, we should have this launch. You also have Mutaya Vanita and Ritu Karidal. These are the two women who were behind the Chandrayaan 2 mission. And Vanita has also been the first female project director. And they've been also, Ritu Karidal is also is part of the Mangalyaan mission, right? Anuradha is the senior most women scientist in ISRO, and she's been working with ISRO for the past 35 years. She's actually been part of the GSAT 12, GSAT 10 program, as well as various other activities at the ISRO Center. Nandini Harinath, most of you all would be actually familiar uh, with her picture. She's the project manager of the MOM mission, which is the mission to Mars, the Mars orbiter mission, and she's already got very famous for her contribution. She's been with ISRO for more than 2 decades and very active in the activities. Sita Somasundaram has been the program director at the Space Science Mission. She's actually involved in Mangalyaan. She's also been very actively, she's the project director of Astrosat. Astrosat is a satellite of ISRO, which basically has telescopes. Okay, the whole mission is only made up of telescopes. There are 3 X-ray telescopes, one ultraviolet telescope, and one optical telescope. This was launched in 2015, and Dr. Sita is actually the program director for the Astrosat mission. Other than that, even in the astronomy community, we had the previous president of the Astronomical Society of India. This is Professor G.C. Anupama. She works at the Institute of Astrophysics in Bangalore, and she was the first female president of the Astronomical Society of India. Right. We also have here a picture of Annapurni Subramaniam. She's the director of the Indian Institute of Astrophysics in Bangalore, and also very active astrophysicist. Here's another very well-known astronomer who's called Chanda Jog. She works in the Indian Institute of Science. Now, I'm not going to mention many more, but there are obviously many more active women astrophysicists who are working in different institutes in India and contributing to astrophysics in India. Right? So we do have a lot of women here too. But what are the statistics? Let us look at what are the statistics about women in astronomy, right? So let us see that. And if you see this, there is what is called the International Astronomical Union, which is the largest professional body of astronomers. And this is a picture of the General Assembly, which is the big meeting which they had in 1928, which is of the Indian Astronomy of the General Assembly. And if you look at this image, the circles you see in this image are the only women who attended the General Assembly in 1928. So you can count that 1, 2, 3, 4, 5, 6. So for this whole General Assembly, which was there in 1928, you had only 6 women who attended the General Assembly. This is the largest meeting of professional astronomers in the world. Now, gradually, obviously, the representation of women has been increasing. You can see over here also, just men. They're just only men. And if you actually see the General Assembly, then in 1932, 4 years after that, you can see that, yes, there are already a certain more number of women, gradually increasing number of women, but still not very large, right? Later on, we had the second female vice president who was from China. This is 1988 to 1984. and this is Yeshua. And gradually you can see that the stats, if you see in 1939, only 10% of the members of the International Astronomical Union were women. Gradually, as things have been changing, even in 2021, the percentage of women is only 20%. Okay. If you make such a plot in terms of age distribution, things are a little bit more, more encouraging. If you see in terms of age limits, then you'll see that in younger generation, you have a better representation. You have almost 35 to 40% of the members are women. But in the older generation, we still have only 20% of women, right? Which clearly shows you that there's a problem, right? Now, obviously, there is no issue about capabilities, right? In the beginning, I told you so much about women astronomers, basically to convince you that there's nothing about the capability of women, right? Obviously, they are equally capable of doing astronomy, right? So, if you look at these two plots, this is a plot here for physics and this is a plot for astronomy, which are both very similar. If you actually see that when you come to high school students, you have almost a 50-50 divide of female and male students, right? You have female slightly less than male, but still 45-65%, close to 50, right? As you go up the ladder, when you go to bachelor's degrees, you see that then only 25% of them are women, 75% are men. And then as you go to PhD degrees, it further changes. And then when it comes up to recruitment, in the terms of assistant professors, you barely have 10%. Associate professors, full professors, you have barely 5%. Now, this is what is called the leaking pipe problem. In the sense, when we start off, you have an equal amount of women and men. But then as you proceed, go up the ladder, if you see in the say number of PhD students, in the number of faculty in astronomy, in the number of professors, deans, directors, people at higher positions, you clearly see a very sharp fall in numbers. So this is called the scissors diagram, or it's called the leaking pipe problem, which is there in physics as well as astronomy. It doesn't exist in all branches of science. For example, in biology and chemistry, it isn't like this. In the sense, you do have a good number of women. But somehow in physics, maths, astronomy, these are the fields in which, especially women in higher positions, are really in a very small number, right? So if you actually see, the numbers are really very small. Again, it's another plot to show you the same thing, that if you're talking about students, you have a larger amount of, these are the men, these are the women. But as you go to full professors or go to higher positions, you will see that the number of women is much, much lesser than the number of men. They are like 5%, 10%, while 90% of full professors, deans, directors, heads of institutions, they are all men and not women, right? And therefore, you can see that there's a clear distinction or a difference between the number of women and the number of men, right? Again, if you look in, this is the data for US. In the US, if you see the US population, and this is a plot of the US people in science and engineering, in principle, this plot should be a reflection of this plot, right? In the sense, in the same population, you should have similar numbers of people doing various professions, right? But if you see in the US itself, though white male population is only 30%, but 50% of the population of people in sciences are white males. Similarly, though white females in population is 32%, but in sciences it's only 18%, right? So what happens is, you see, is that almost 70% of the population is only whites, right? But obviously you can see in this plot that the other kind of groups, right, other ethnicities also play a very important role in the populations, but they do not play in the terms of their contributions into science. A similar plot obviously can be made for India and various other countries. So what are the key problems? Why do we have this kind of a problem existing, right? So first important problem are stereotypes, right? In our societies and in our minds, there are very strong stereotypes as to what are the things that men should be doing and what are the things that women should be doing. We do not realize it, but often, like in a simple thing like even giving birthday presents, the kind of birthday presents that are given to girls, little girls and little boys, There's a big difference in that, essentially because girls are given dolls and things to color and paint, while boys are given, mechanical things. They are given Lego toys. They are taught how to construct. And so from childhood itself, there's a difference in the way girls are brought up and boys are brought up. So therefore, uh, the three-step process is required. First of all, to educate girls so that they get into careers in STEM. Then the other important thing is recruitment. That when these girls take up careers in STEM, you actually recruit them, give them jobs, right? The other important thing is to retain them, right? So that they hold their positions. Because typically what happens is that if these girls, they later on get married and have children, they often have to drop their jobs or move away, while we have to do something so that they retain their jobs. These could be simple things like childcare facilities at workplaces, flexible working hours, and various other things that can actually help women who have children to continue doing their work. And then what's also important is what is called sensitization. There has to be gender sensitization at work so that people are conscious of their colleagues at work and understand their requirements as well as their needs, right? So some kind of gender sensitization is also something which is very important to be done at workplaces. Now, to help do this, the International Astronomical Union set up a working group on women in astronomy. So I am the co-chair. This is the chair, Mamta Pomier, and we have a working group for all these people over here. And we try to do things in the International Astronomical Union, which can help women in in doing this, right? So we do basically work on a 4-point program. The first program is about building up awareness and sustainability, to conduct surveys, to collect information, to let know, what is actually happening to women in the community. Another thing which I've been very focusing a lot on is training and skill building. That is, we need to develop resources, collect materials, so that we actually train women on, using software, on developing skills. Basically, with the contention that if women actually have skills, that then obviously the employer will employ them, because they know that this woman knows a certain skill and she can deliver a certain result. So they would be willing to probably compromise on working hours or various things if the woman has skills. If the woman does not have skills, then it would be anyway very difficult for her to actually get herself a position. So it's very, very important that women make themselves indispensable by actually developing certain skills. The other thing is fundraising, to raise funds, provide financial support to women researchers. And then the last thing is about communication and dissemination. We should encourage women to communicate with each other, talk about their problems, talk about their issues, and actually look for solutions to the problems which we face. Because we've already noticed that women almost all through the world, they have similar problems and similar issues, and therefore probably many of these problems can be handled in similar ways in different countries, right? So IAU has been doing various actions to promote women. For example, they know that the fraction of women in IAU is still low, so they're trying to do things to increase the membership of women. Now, what they've tried to do is, especially in the high positions, the present president of the International Astronomical Union is a woman, Deborah M. Green, and you have had many more female presidents, as well as on the executive committee, there are a lot of women. There are also actions to basically to build up role models so that women can actually feel more confident when they see other women in such high positions. There are also various actions to make women more visible. For example, to help them get leadership positions. For example, they are heads of different commissions, heads of different steering committees. It's actually, you keep track of how many meetings, how many speakers are women, how many invited talks, contributed talks are by women, and what is the, various actions to actually increase the diversity. Okay. So even when I use symposia I organize, they try to keep a track of how many women are participating in organizing and giving talks, as well as participants in the symposia. If you actually look at the gender distribution of women, you look like even the developed world, this is North America, Europe, etc., just has a 20% contribution of women. The other parts, some parts of South America, are the ones which have a larger proportion of women. If you see, it has kind of increased, improved a little bit over time. This is 2018. You see, it's slightly improved. So even India has 20%, but we are still not yet there, right? We definitely need larger numbers. You have a whole bunch of countries which have still lesser, 1 to 10%. So, like I said, various actions are being done to promote it. More women in IAU positions, high positions. The working group has been set up. They also keep track of how many women are in symposia. When we have the General Assembly, we have a Women in Astronomy lunch where people actually discuss issues about women. There are mentoring sessions organized, as well as gender gap studies and various things being done by the International Astronomical Union to handle these things. So here are an example of four IU presidents who are women. This is the present president, Deborah Ungrid, and you have the previous ones also, Ibn, who's also a woman, and you have got more women as presidents, right, as role models. If you see the IU officers also in 2015 to 2018, 3 out of 4 people are women. The 2018 to 2021, again 3 out of 4 women. The present one has a perfect 50-50 drop, 2 women, 2 men, and this is the ideal situation which we would like, where there's equal representation without any discrimination. Similarly, even the female general secretary, we've had them as women. Uh, Division presidents, there are various divisions in the International Astronomical Union. And the division presidents, there are 5 women and 4 men, right? It is well represented. And similarly, like I mentioned, in scientific meetings, they keep track of how many women are participants, how many invited speakers, and how many contributed speakers are there for the different symposia which are organized by the International Astronomical Union. And this obviously needs to be followed for any other kind of meetings which we even have in our country, where we keep track of how many women. You see that this is the 50% mark. We are still not yet at the 50% mark, right? So we still have to definitely do more work in this direction. Like I mentioned, we have the Women in Astronomy lunches where women actually talk about their problems. And we also have some things which are done which are in gender, uh, not based on gender. The International School for Young Astronomers. This is open for men and women. And you see that even women participate in this. This is basically on training and skill development. There are also PhD prizes. Again, this is without discrimination. This is open to both genders. And you can see that there are women also who do win these prizes. Right? There's the Gruber Fellowship, again for young astronomers, without reservation for women. And you see a good amount of women also getting these prizes. There is even the IAU Women and Girls in Astronomy, which are various activities conducted specifically during this period, and various efforts which are being taken, right? So we are definitely doing a lot of efforts to actually improve the situation, not only for women, but also for all the underrepresented groups which are there. And we do hope that in the next 100 years, the IAU will have a gender, independent thing where you have various kinds of people taking part, irrespective of their, it's a diverse group, inclusive groups. And yeah, so like I mentioned, the 4-point program, which we already have. So let's all hope and work towards an ideal world where people can actually follow their dreams, pick up their wishes. There's a freedom of choice in the sense if somebody wants to do astronomy, they should be in a position of doing astronomy, equal opportunity for everyone, where we actually have no requirement of reservation, where you can actually have in gender independent prizes, positions, and where the individual is non-gendered. So that's the kind of world which we'd actually like to, look up to, where you won't have this kind of discrimination, and you can actually discriminate. So I'll actually wind up with this, where we can actually, uh, we can actually just look at, independent of your gender, men, women alike. everybody can pursue whatever career they would like to. And I'll end with this quote of Henry Poincaré, that astronomy is useful because it raises us above ourselves. It's useful because it's grand. It shows us how small is man's body. In this case, this should also have woman's body. How great her mind, since her intelligence can embrace the whole of this dazzling immensity, where her body is only an obscure point, and enjoy its silent harmony. So I will wind up with this, and I would end with this note that though we know that women are underrepresented in astronomy, we do hope that in times to come, since there are various efforts being taken to actually encourage women in astronomy, we do hope that there'll be a change and there'll be a much better representation of women in astronomy. I would also like to add that as part of the citizen science projects, right, there are on my YouTube channel as well as with the group of Sovanacharya sir, you could actually have a look at the various, the various um, citizen science efforts which women can participate in, which can help them, initiate into a career into astronomy. So I'd end with this and I'd be open to taking questions. Thank you.
Thank you, ma'am, for this wonderful presentation. Now I think we can move on to our Q&A session for today. So participants, if you have any questions, you can please feel free to ask your questions. Also, you can type your questions in the chat, then I will read out the questions. No problem with that.
I don't see any questions on the YouTube also. Thanks, Amritanshu. Thank you. Manish, maybe you can read out what Amritanshu has written, or
Yes, ma'am. So Amritanshu has written a gem of an address by Priya ma'am. Srishti astronomers under Priya ma'am is already doing a lot in the field of citizen science. Hope that the issues we put forward on this forum by Priya ma'am shall be considered both at amateur and professional level. Thank you, Amritanshu, for this. And also, we have another question in YouTube chat. So, Dr. Salil Gupta have asked, how do we learn about women astronomers from India and their contributions?
yeah. So actually, there is what is called the Astronomical Society of India, right? And if you actually look at the members list in the Astronomical Society of India, you'll actually be able to see most of the astronomers who are there in the country, right? So I'll just, if I can show it to you, 1 minute. So yeah, so the best way is to go to the site of the Astronomical Society of India, right? And I can show it to you. So yeah, So this is the Astronomical Society of India. You can go to this website and you can see various things about the activities which are happening in the ASI. And if you actually go in for members, you'll get a membership list and you can see the list of life members. You could also see various other lists, but if you see the list of life members, you will actually find a big list over here, right? So you'll actually see it over here, right? And so obviously it has male, females, but you can actually from this find out various members. You can also have a look at the various activities which are on over here. And there are meetings held. There are also some committees, of which one which is interesting is the Public Outreach Committee. And you can actually see various activities of the Public Outreach Committee. I earlier worked with the Public Outreach Committee. Now I'm not with them. But you can actually have a look at their activities, and that could be quite useful.
Thank you, ma'am. We have another question in on YouTube chat. Navanita Nandita have asked, I want to become an astrophysicist. I am in ninth standard now. What should I do?
Yeah, so basically you need to study physics and maths. Okay, lots of physics and maths. You'd essentially need to do a master's in physics, and then you can go in for a PhD program in astronomy. So basically that means a lot of studying. Yeah. So
Okay. Sure. Okay, so we have another question from Emily Richardson. As a housewife, can I contribute myself in the field of astronomy?
yes, definitely, you can. So there are various citizen science projects in which you can participate. So one of the co-organizers of this is Sovan Acharya sir, and he basically runs a lot of citizen science projects. So you can participate in the sense of detecting asteroids or looking for planets or classifying galaxies or various. So there are many, many citizen science projects in which you can participate. So contact Sovan Acharya sir and you will get to know a lot of these citizen science projects.
Amritam, do you have any question? Please feel free to ask.
Yeah, greetings all. And first of all, greetings on the occasion of this all important day. And thanks to the organizers and the wonderful speaker of the day, Priya ma'am. I hope I am audible to you all. And rather than a question, this is a point as a co-chair to the women's wing to be put in front of Priya ma'am. Ma'am, as we know that at the university level, there are different courses of women empowerment. Even if you go to the field of, you can say, arts, commerce, or science. So my suggestion is like this: you can take it in your record. That can there be, you can say, a certain chapter or a certain, you can say, unit of the role of the women scientists being played in the development and the nourishment of science and technology that can be taken seriously as academic in the course on the women empowerment field.
So yeah, there is work done in that direction. There isn't a specific committee, but definitely all universities do have, women studies cell, etc. They don't specifically focus only on sciences, women in various fields. But yeah, that would be a very good thing. That would be a really positive thing if that's done. That would be
Thank
good.
you, ma'am.
Yeah.
Okay, so lastly, I would like to request everyone, if you have any other question, please feel free to ask. Okay, so I think we don't have any other questions. So we'll be moving towards our conclusion for the session. Firstly, thank you, ma'am, for this wonderful session and letting us know all about this wonderful informations in the past. And also, I think we learned a lot from this session about how women are contributing in that field of astronomy from the very past also. And so thank you for the session. Secondly, I would like to thank Sovan Acharya sir for and SS Citizen Science Group for helping us conducting this session. And lastly, last but not least, I would like to thank all our participants for attending the session, and also all our YouTube subscribers for attending the session. Thank you, everyone. And with that, we'll be ending our session here for today. But lastly, I would like to request everyone to turn on their camera one so that we can take a picture. Thank you, everyone. I think with that, we can end our session here for today. Thank you, everyone.
Thank you. Bye-bye.
Thank you. Thank you.